the rest of the output that will be used as investment, right? So that will be the saving rate, or you can say investment rate in the solar model times the output per worker. So finally, we have the complicated terms here, RT and WT. But basically, you can use the Euler theorem. Okay. So last week we talked about actually this is an assignment, right? But you don't need to turn in your answers to me. Okay. So basically, if you use the Euler theorem directly, you should have this answers. Okay. But well, if I do not know Euler theorem at all, well, still we can solve for RT and WT. Why? We know YT can be written as A times KT alpha, right? So this is coming from this production function, right? So we have the Kolmogorov production function. So we divide each term of this equation by MT, then it gives you this expression, right? Suppose I know nothing about the Euler theorem, but I'd like to show you that still we can solve for WT and RT. So we begin with the first autumn condition, right? So we know that based on first autumn condition, WT should equal to the marginal product labor. So we should have this, right? So, well, immediately you can combine it together and rewrite this equation as this one. Right? So, by definition, the ratio actually is referred to as the capital per worker and is denoted by the lowercase a, k, right? Also raised to the power alpha, okay? How about the interest rate? Again, according to first autumn condition, or the factor price for renting capital should equal the marginal product of capital, right? So this is optimal condition of the first problem. So according to first autumn condition, you know the factor price R should equal to the marginal product of capital. So it gives you this. Again, you can combine these two terms together, so it gives you this. Okay, and we have. Okay, so well, so you can use Euler theorem to do this exercise, but if you are not familiar with Euler theorem, how apply Euler theorem to solving these two expressions, still you can stick to first autumn conditions and use these autumn conditions to algebraically solve for RT and WT, those expressions, all right? So basically, all we want is to lay out all the equilibrium condition and express the variables under your consideration as functions in terms of KT. Okay, so again, once you know the time pass of KT, the capital per workers time pass, now you can use the other equations to solve for Y, C, I, R, and W. Okay, so they just describes the equilibrium of the solar model. All right. So now next, I would like to show you that. So how to graphically how to use a graph to analyze the dynamic path of the solar model before we jump into the mathematical technique. Okay. So before I show you the graph, I can actually use the central equation that describes how capital accumulates over time. Okay, and this actually serves as a powerful tool for your later graphical depiction and also analysis. Okay, so now go back to equation 9. So now I would like to know how will KT plus 1 react to the changes in KT, right? Because it seems that, well, the Kaplan-Stopper-Walker actually drives the income growth over time, right? And also affects how the other variables look like, okay? So to see this, we take the derivative of KT plus 1 with respect to KT, right? So we use equation 9, right? So now you have equation 9 in mind. So we take the derivative of KT plus 1 with respect to KT, right? So the derivation gives you this, right? As e times f1 KT plus 1 is still type, okay? So indeed, once you have greater amount of KT, you should have greater amount of KT plus 1. So clearly, the sign of derivative is positive. So that KT plus 1 is an increasing function for KT. But as you can see, at a decreasing rate. Why is that? Because as you can see, F1, F double prime actually is negative, right? So of course you can see that KT plus 1 increase in KT, but as KT gets larger and larger, the incremental change gets smaller and smaller. Despite the fact that the incremental change is positive, but the positive amount actually gets smaller and smaller as KT increases, alright? So we said that indeed KT plus 1 is increasing in KT, but at a decreasing rate, alright? That is captured by the assumption that the marginal return must be diminishing as we increase the amount of the input employed, right? Well, it is something that I guess you already know, alright? But I like to introduce you some additional conditions that somehow guarantee there will be a unique and stable equilibrium or the steady state solution, okay? So this is called another condition, alright? So then actually there's kind of the technical assumptions, okay? So this is something that will serve as guaranteeing a unique and stable solution, alright? So before I show you that, so now let's take a look at what is true in another condition looks like, okay? So the first part of another condition says that once k is really close to 0, then you should observe that up and from the marginal product of capital goes to infinity, okay? Well, actually it holds, this another condition holds under various production functions, including the Cobb-Douglas type, okay? So later we're going to verify it, okay? The other condition says that, sorry, I made the typo here. This is not 0. This should be infinity, okay? So if k is really large, then we should observe that, well, F1, the model product capital should be close to 0, all right? So if I draw KT plus 1 against KT in this figure, so well, the variables of my interest will be KT and KT plus 1. So I just have KT on my horizontal axis and KT plus 1 on my vertical axis, okay? So actually this curve depicts KT plus 1 against KT, again based on equation 9, right? So this equation exactly describes how K Kaplan-Stopper-Walker evolves over time, right? So again, this curve KT plus 1 starts from the origin, right? Because as you can see, once you have KT equal to 0, KT equal to 0, it gives you 0, okay? So this curve starts at the origin. And we know that once you have greater KT, of course